So we have discussed in the previous class the weak form of the weighted residual, but converted to piecewise continuous trial functions, not one single trial function valid over the entire domain 0 to L, but defined in bits and pieces. Obviously, the bits and pieces do not have to be of the same size, right? But for convenience, I am probably going to assume that they are of the same size, so that your formulation details do not look too cumbersome. Okay. But conceptually, we know that the bits and pieces can be of different lengths. Over each bit, you can define a shape function or a trial function. They will be piecewise continuous because they would be continuous within that element, but across elements there may be discontinuities in the slope and higher order derivatives. So we would take up this generic second order ODE and try to develop our first finite element formulation. So you please follow how I go about doing it systematically. You would also notice that I will not worry about whether the problem is from heat transfer or structural mechanics or electromagnetics or any other domain. So I will take the second order ODE as a representative equation. We can always work out special cases of that as heat transfer problem or as a electromagnetics or a structural mechanics problem. So we will look at the generic structure and the flow methodology. Okay. So the generic equation I take will be, please see if you are able to read what I am writing on the board. So I will take generally so A d squared f by dx squared plus B df by dx plus C f of x plus some source terms g of x is 0. That is your generic second order ODE. It has the source term, which is the exciting forces, heat fluxes, electromagnetic potentials, and whatever. Okay. That is g of x. That is causing a response which is governed by this second order differential equation given as A times d squared f by dx squared plus B times df by dx plus C times f of x plus g of x is 0. A, B, C are some constants. A, B, C constants. Okay. Now, being second order differential ODE, it would have two boundary conditions. I am generally assuming that to be f of 0 is equal to alpha df by dx at x is equal to L is equal to beta. These are our two boundary conditions, let us say. So this is how the problem is given to us. Now it is easy for you to see immediately if B is 0, say even C is 0, then what happens? A is say AE, F is say U, then AE d squared U by dx squared plus G, let it be represented by Q of x is 0. So this will be a deformation of a rod. Okay, this would be deformation of a rod problem. Okay, if B is 0, if A is K, coefficient of thermal conductivity, B is 0, C will be minus PH by AC that we discussed, and correspondingly G of x, F is T, etc. So you can write it as K d square t by dx squared plus or minus whatever ph by AC t minus t infinity plus q of x, if you want to put some heat source, is 0. That is the differential equation we wrote for heat transfer, one-dimensional heat transfer, right? So this would be a heat transfer problem. Which has conduction K and then convection H. Okay. We solved the example problem of a fin using such a differential equation. Okay. So these would be special cases. I am going to come back to them at the end once I formulate the finite element for this generic equation. Okay. So let's see how my formulation goes. So we are looking for a solution f of x, but that would be an exact solution. So I am going to look for an approximate trial solution f hat of x, correct? That's our discussion for this whole course. So I am going to look at, let f be approximately equal to f hat of x. Please also note that I am using now capital X because when we said piecewise continuous trial function approximation for a weak form, we introduced local coordinate frames. That would be small x varying from 0 to small l. This is capital X, which is a global x coordinate which runs from 0 to capital L. So if you want, you can write it down somewhere here. Capital X will go from 0 to capital L. Small x will go from 0 to small l. Okay. So let f is f hat of x. I am going to put integral 0 to L w of x into a d squared f hat of by dx plus b df hat by dx plus c f hat plus g. This is the domain residual. This is the domain residual. Weighted sum of this, w is a weighting function, r d of x dx equal to 0 with the condition, same conditions, f hat of 0 is alpha df hat by dx at x is equal to L is equal to beta. Okay. So this is your, what did we call this? Weighted residual, Galerkin's weighted residual statement. Galerkin comes when we choose W. So this was the strong form of the weighted residual statement. So I am going to write here strong form. Strong form weighted residual method. Okay, fine. Now I am going to apply integration by parts and get the weak form. Let me see how that will look. So what did we do for weak form integration by parts? We did on the first term. So that is w of x df hat by dx L minus w of x df hat by dx at x is equal to 0 minus, I am straight away writing these things because you have already done it in the previous classes. Okay, practice problems also you have solved, so you know how the equations look like. 0 to L a dw by dx df hat by dx dx. Rest of the terms I am not going to touch. So they will be just the same, 0 to L w times b df hat by dx plus cf hat plus g dx is 0. Okay, fine. I have done integration by parts on the first term. Rest of the terms I just carry it as they are. On the boundary conditions, we have said where f hat of 0 is alpha, so that remains the same. And since at x is equal to 0, the function is prescribed, we are going to ask for the weight function w of 0 to be 0. This is our weak form, so to say. Okay. Is that clear? Any doubts about this? You have solved it in the previous class, right? Any doubts? Okay. Shall we take it as understood? Okay. Now what we did, because w of 0 is 0, so I am going to strike this off. Because w of 0 is 0. Okay. And df hat by dx at x is equal to L has been prescribed to be beta. So I am going to, sorry, there is an a missing here, because the first term has a, so we need to carry that a. So this becomes beta, that is what is prescribed. Okay. So keep these points in mind, and then we will continue the derivation or formulation further. Is this clear? Okay. So it will be a w of L beta, that's one term, minus integral 0 to L a dw by dx df hat by dx plus integral 0 to L. I am just rewriting after substituting for boundary condition. Or in other words, this can go that side. So integral 0 to L a dw by dx df hat by dx is equal to integral 0 to L This is our weak form. Weighted residual statement. Now, when we introduce piecewise continuous trial functions on this, each trial function being defined only on that element. So, I do not have from 0 to capital L, but I am going to take f hat to be defined over that element only, right. So, that is what we did in the previous class, okay, using linear, quadratic, cubic, whatever shape functions or trial functions, interpolation functions, whatever name you give. So, I am going to write this as a summation over n elements. So, exactly the same statement, but I would write it as sigma 1 to number of elements Please see the same statement Okay, so this would be piecewise continuous trial function weighted residual method. Okay, this statement would be when you are doing piecewise continuous. Integrations is a summation series, so we are going to do summation not from 0 to capital L, but over each domain and then add it up, whatever total sum you would get. Okay, so that is all I have done. There is nothing from here to here. Okay, till now I did not bother what is the finite element that I am going to be using. So I did not bother whether I am going to use linear shape function, trial function over the pieces, quadratic or cubic or anything. Okay, so now we will define the element. The simplest element to be worked out is the linear element, linear shape element functions, linear interpolation of the displacement or temperature or whatever variable you have. So linear variation. So I am going to formulate first using this equation, assuming that f hat would be linear. If f hat is linear, then w also will be linear. First derivatives will be constants. So that would be the simplest element that I can formulate. What is my strategy going to be? I am going to define this element. In principle, I can choose different types of elements at different locations in the total domain. Supposing I think that there is significant of loading happening at a particular location. So there is a strong variation in the displacements and correspondingly the strains and the stresses, which cannot be captured by the linear element trial function. So there I could choose quadratic or cubic. Okay. So sharper variations of the field variable, you could choose higher order shape functions. Where there is not so much variation in the field variable, I could choose linear. Okay, so I could change this. I am not going to do all those complications right now. Right now I assume that everywhere from 0 to L, I am going to use linear shape functions. All the elements will be of equal size, just for simplicity, so that you get to understand how the formulation goes. Then we can introduce all these complications. Okay, so I am going to formulate this equation, how it would look if I am doing just say an assembly of two finite elements, so that I could have used even one, but that does not give you the scope of the piecewise continuous trial functions. So the minimum number I need is 2, so I would use two finite elements, linear elements, and then formulate the equations. So follow how I will do this. Is this clear up to this? Any doubts? Okay, so let's take this equation now, and then I will focus after defining the element on one term at a time, so that it is easy for us to progress with the calculations. So what the linear element now define so linear element. When I say linear element, the linear term refers to the interpolation functions, shape functions or trial functions. So it is a straight line, some function value f I hat to f j hat, x is 0 here, small x is 0 here, small x is small l here over the length of the element, and f of x is given as This is what we discussed in the previous class. That is our linear element. So, the function value at any point in between is interpolated from the values of the function at the nodes. There are only two nodes. So, you can only interpolate linearly between the two values fi and fj. So, I am going to interpolate it by a rule of mixtures as 1 minus x by L at any location x. At any location x, f hat of x is linearly interpolated from this value and from this value, function value at this node. So, fi hat, fj hat, 1 minus x by L. So, the influence of this goes down as we go here. The influence of this nodal value increases as we go away from and approach towards node j. Okay. So, this is my, therefore, df hat by dx is, if you differentiate it with respect to x, you will get it as minus 1 over L fi hat plus 1 over L fj hat, or simply the slope of the line. So, fj hat minus fi hat upon L. That is simply the in that element. So, if I take two elements, let us take, now that you have defined the element, this is the element I am going to use, I am going to formulate the equations for this linear element. Okay. Let us take a, let us now define the mesh or discretization. That means, how I am going to divide this total length from 0 to L into how many elements. Simplicity, I am taking just two elements. Okay. Two elements of equal length. Okay. So, I will substitute L by 2 later on at the end, but two elements of equal length. That is for simplicity. Okay. So, f of x over that mesh, that means, let me draw the mesh for you here. So, if I am saying that it is 1, 2, 3, first element, second element, this is capital X is equal to 0, capital X is L, that is a total domain. I have subdivided into two elements, 1 and 2. This is first element, this is second element. Okay. So, over this f hat of x is now defined like this. So, you please see how it is defined over that, because each element, it is defined only for that element, right, this interpolation function. So, I am going to write this, please see how it would look like. F hat of x is 1 minus x by L f1 hat plus x by L f2 hat if you want, if you are, because you are doing it for the first time, first element, to feel comfortable, you can write plus 0 into f of f3 hat in is equal to x by L this would be the counterpart. So, 0 times f1 hat plus 1 minus x by L f2 hat plus x by L f3 hat Okay, this is the important step you should feel comfortable with. Once you feel comfortable with this thing, the next is going to be how I choose the W. Then rest of it is substitution, differentiation, integration, and so on and so forth. Okay, so please follow this. Yeah. How did I get this? This is clear? Correct. So I am assuming that f hat of x is, say, linear function. So C0 plus C1x. Then at x is equal to 0 in the element, it should be equal to f1 or fi. At x is equal to small l, it should become equal to fj. So I get this when I substitute. Okay. So this is clear. Once you have got this, now in this element it is so. But now I have a mesh of 2 elements or 20 elements or whatever. Okay. So f of x is f hat of x, our total solution, okay, over 0 to L over the whole domain is defined, okay, in each element only through these interpolation functions. Okay. So when I am in the first element, it is this much.
So how did you get those values? Like 1 minus x by c.
Pardon me?
How did you get those values? 1 minus x by x by.
That is what I got here. That's what I got from here. A linear approximation. Linear trial function, if you assume, this is how you would get it. Okay. Then I am assuming therefore linear, so I get this for f of x in the first element. It is interpolated from its 2 nodes. You have f3, f4, f5, whatever 200, it doesn't matter. Okay. It is interpolated for all x values in this element from only the 2 nodal values. Okay. This has very significant computational implications, which we will learn more as we formulate the entire matrix of equations. Okay. So we will come to that aspect later, but right now you will notice that f of x in that element is interpolated only from the 2 nodal values f1 hat and f2 hat. When I move now to the second element, it is interpolated from f2 and f3 only. I don't know these values f1, f2, f3. I need to find them. Okay. For a 2 element mesh, I need to find 3 values f1, f2, f3. That means how many equations I need to generate? 3 equations, because I have 3 unknowns. That one single differential equation, I am going to now try to get 3 algebraic equations. So this whole process we are doing through finite elements is to simply convert that one differential equation into many algebraic equations. Each algebraic equation is valid or centered around that particular node. So it will, you will have 3 equations in f1 hat, f2 hat, f3 hat. 3 equations, 3 unknowns we can solve. So that's how I am going to propose the whole formulation. Okay. So is this clear? How I write f? Once I have written f, Galerkin method has prescribed how to choose w. So w will be the coefficient function for f1 hat, f2 hat, f3 hat. So w will get decided based on this. That's why I am re-emphasizing, this is a step you should feel comfortable with. You should understand, you should be able to do it given any problem, new problem that you are solving, you should be able to do these steps. Once you get this f hat of x, then w is prescribed, because we are using the same interpolation functions for weight function also as per Galerkin's weighted residual method. Then I am going to just simply substitute in the piecewise continuous weak form. That's my strategy. Is that clear? Okay. So let me keep this part and then see how I will do it. If I were to change this element, rather than linear element, I do something else, then these shape functions will be different. We would, once you are comfortable with all this, I am going to formulate the quadratic element. Then these shape functions or interpolation functions will be quadratic. Then here you will get quadratic terms. Weight functions will become quadratic, etc., etc. But procedure template is identical. Okay. So let's see how we proceed to formulate with linear functions. So once we have this, first the process was that given differential equation, we wrote the strong form weighted residual, then weak form weighted residual, then piecewise continuous weighted residual statements, then we defined the element, then we defined the mesh. Okay, that's the template we are going to follow right now. Okay, so once we have defined this, so there will be three weight functions. W1 of x is 1 minus x by L in what multiplies F1. So in first element, and it is equal to 0 in the second element. Okay, 0 here. So 1 minus x by L, 0. Now W2 will be x by L 1 minus x by L. X by L and 1 minus x by L. What multiplies F2 hat? That's all I am choosing. Then W3 will be 0 and x by L. These are first row corresponds to first element and this corresponds to second element. Okay. Is this okay? So I am going to substitute now in the piecewise continuous trial function weighted residual method. Okay, let's see how it goes. So I am going to write this piecewise continuous trial function weighted residual equation 3 times now. First time with respect to W1, second time with respect to W2, third time with respect to W3. Clear? Correct, no? Okay. So I am going to write now. So take W is equal to W1. Let's focus on the LHS first. Integral 0 to L A dW1. First term I will write fully, rest of them I will directly substitute. Right? df hat by dx. So this would be for us 0 to capital L if you want to write, capital X if you want to write. That's given as 0 to L over the first element. W1 is 1 minus x by L. So dW1 by dx is minus 1 over L. This is anyway F2 hat minus F1 hat by L dx plus integral 0 to L A times W1 in the second element is 0. So that's dW by dx is anyway 0. So in the second element, right? So F3 hat is this okay? Which one? This one? Yeah. 0 to capital L, that is what we need to calculate, right? I am now splitting it as integration over first element and then integration over the second element. First element, when I take W1, dW1 by dx is minus 1 over L. Over the second element, W1 is 0. So dW1 by dx is anyway 0. But the dF by dx has changed. Okay? Fine. So if you do this, this is simply, this goes off. Okay? This is simply, dx is, this whole thing is a constant. Right? This whole thing is a constant. So dx is L. So L goes off. Please see if okay. Fine. I could do with respect to, I am focusing on the left hand side terms. Then I will take up right hand side one term at a time and work it out. Okay. So I will write it here directly, 0 to L A times dW1 by dW2 by dx. W2 is x by L. So dW2 by dx is 1 over L. Please see how I am writing. With respect to W2. Okay. 1 minus x by L. So d by dx, I need dW by dx, right, on the left hand side. dW by dx will be minus 1 over L and 1 over L. X by L is dW by dx becomes 1 over L. Okay. So this will be, this is again same, dx becomes L, L goes off. So A by L minus F1 hat plus F2 hat. This is minus, so plus F2 hat. Okay. Take it easy, slow, go through what we are doing. W2 now. So dW2 by dx in the first element, dW2 by dx in the second element. dF hat by dx in the first element, dF hat by dx in the second element. Okay. So it is, this whole thing is a constant, this whole thing is a different constant. So integral dx is simply L. So I get this. Okay. Fine. Any doubts? What would, could you do it for W3 and tell me what you get? If W is W3, what do you get? Left hand side will be what? Can you guess what it is without doing? Don't do it, don't rush to do it. Just see what we got. Can you guess what would be A by L? A by L will be there. Okay. F3 hat minus F2 hat. Okay. So this is an inherent advantage of using local coordinate frames. The calculations have become kind of repetitive. You know how the calculations will go, how final result will look like. It's just repetitive set of calculations. So F1 minus F2 here, F2 minus F1, F2 minus F3. I have not added them intentionally. 2F2 I did not write. Then F3 minus F2. So it's the same thing. You see that? If you want, you can keep it like this. Okay, whatever way. So W1, W2, W3, I have now got the left hand side clear, okay, of the finite element mesh, and we have already got the left hand side equations for the 3 equations. Now let me work out the right hand side. Fine. So right hand side, I will go one by one terms. So first term, okay. First term again I am going to do with respect to W1, W2, W3. So I will put it together all the equations at the end. So first term is integral 0 to L, so to say, W B df hat by dx. Okay, this is what you have got. You need to compute this. So we are going to look at it with respect to now W1, say, or I will write it here and keep it so that we remember what that term is. Integral 0 to L W B df hat by dx dx. This is what I need to compute. So W is W1. This would be integral 0 to L. W1 in the first element is 1 minus x by L B times df hat by dx in the first element is f2 hat minus f1 hat by L dx plus integral 0 to L. W in the second element W1 is 0 B f3 hat minus f2 hat by L dx. So how much is this? This is 0, so this goes off. B into f2 hat minus f1 hat by L is a constant. Integral of 1 minus x by L dx will be how much? Just do it. B into, so this will be integral 1 minus x by L dx. So this becomes x, this becomes x squared by 2, right? So 0 to L, so this is L minus L squared by 2L, or L minus L by 2, L by 2, L I will cancel off, so B by 2. So simply this is, please see if it is, this is what we are getting, okay. Okay, fine, check it. With respect to W2 now, integral 0 to L, first element it is x, first element W2 is x by L B times f2 hat minus f1 hat upon L dx plus 0 to L 1 minus x by L in the second element B times f3 hat minus f2 hat upon L dx. This will be, this is a constant again. So x by L dx, so L squared by x squared by 2L, L squared by 2L, L by 2. L cancels out, B by 2. Okay, I would just write it slightly differently, because this here also I will write it slightly differently. Minus f1 first. Please remind me to write f1 thing first, then f2, then f3. minus f1 plus f2 hat, then minus f2 hat plus f3 hat. Because integral 1 minus x by L we have already done here. So I know that it will be simply b by 2 times. Okay. With respect to W3, integral 0 to L, first element it is 0, b times f2 hat minus f1 hat by L dx plus integral 0 to L x by L b times simply b by 2 So you would see how the computations and the results are flowing with respect to first element, with respect to second element contributions. If you see b by 2 minus f1 plus f2 minus f2 plus f3, okay, minus f1 f2 minus f2 f3. So if you see how the calculations are going, or even at the left hand side, so you would notice that it is very similar computations for the first element and the second element. I just have to keep track of the nodes which the element is connecting. First element connected 1 and 2 nodes, so I got minus f1 f2 minus f1 f2, but second element connected 2 and 3, so I got minus f2 plus f3. Second element connects 2 and 3 nodes, so minus f2 hat plus f3 hat. So once I understand this, how the calculations are flowing, so actually speaking, I don't need to do all detailed calculations. Okay, I can do for one element, and then I can see easily how the other elements calculations will look like. I can write it down. Okay, we are not yet there because we have not yet become so conversant, familiar with the calculations. So we are doing this whole thing patiently. But this is not how I am going to do in future. In future, if I know this, then I am going to simply write. Others will be like this. Okay, I will write it out. Okay, you should also be able to do it in future for different elements that we would formulate. Okay, so for the first element, I am going to work out completely and show you how the structure of the calculations, how the template will go. Is the same template irrespective of what is your starting point. Let it be second order ODE that we have started with, or some other differential equation, whatever problem, physics, structural mechanics, fluid mechanics, heat transfer, electromagnetics, it doesn't matter to us. This is how all these powerful software are able to solve multiple disciplines problems in one software environment. Okay, fine. So left hand side, first term is done. Now I'm sorry, right hand side, first term is done. Now I am going to go to the second term and then the third term and so on and so forth. Is the flow clear? So would you like to attempt and tell me what would be the second term equation? W C F hat. Okay. In the meanwhile, I will be writing down just these things so that I will need them in future. So I will write them down. You can be doing the second term on the right hand side, W C F hat. C is a constant, W would be this, F is the expression we wrote. So let's see how I am getting. Is that okay? Would you attempt it, please? Let me meanwhile capture whatever we have got so far on the board. Okay, so I am going to erase all of this just to keep the results. So this is my first equation, this is my second equation and third equation. L minus F2 plus F3, correct. Now right hand side, first term I already have, B by 2 minus F1 hat I am just capturing whatever we have done so far into an equation form. In the meanwhile, you will be working out the second term. B by 2 minus F2 hat plus F3 hat. This is the right hand side first term. Now, do we have the second term so far? So, I am going to say it is be the second term. So, what I am aiming to get is 0 to L W C F hat dx. This is what I want to get. So, I am going to write with respect to W is W1. So, I am going to write integral 0 to L 1 minus x by L in the first element, C times F is what? 1 minus x by L F1 hat plus x by L F2 hat in the first element dx plus integral 0 to L W has 1 has become 0 in the second, but it's okay. It's a good idea to just write it down so that you see how the terms are coming. Now you can give me what is the result. This will go anyway because this is 0. So this will go. So C times 1 minus x by L into 1 minus x by L dx. So that's how much? Integral of 1 minus x by L squared dx. L by 3. Okay. F1 cap plus F2 cap. F2 cap. F2 hat. Okay, very good. Now W is W2. 0 to L 1 minus W2 is x by L, sorry, x by L in the first element, C times dx plus integral 0 to L, x by L will become 1 minus x by L, C times dx. Can you guess what would be this integral? C times, okay, it is same terms, 1 minus x by L squared or x by L into 1 minus x by L squared. So very similar terms keep coming in the integrations. How much did you get on the right hand side, second term for W is equal to W2? C times okay, C times anyone could complete? L by 6 F1 cap plus F2 cap by L by 3. Yeah. Then plus again. Okay, good. If anybody gets a different result, please alert us. Okay. So that we know if we have made any mistake or. Then W is W3. Integral 0 to L, 0 in the first element, right? C times plus integral 0 to L x by L C times dx. This would be C times if these are correct, assuming that these are correct, what would this third term be? L by 6 F2 plus L by 3 F3. Okay. If somebody got anything different, you please alert us, tell us right now. Okay, so I am going to now capture these three right hand sides onto that equation that we have got. Okay, so this is 1 plus plus plus. What did we get? C times, first was C times L by 3 F1 hat plus L by 6 F2 hat plus 0. This is C times L by 6 F1 hat plus L by 3 F2 hat plus L by 3 F2 hat plus L by 6 F3 hat. This is C times L by 6 F1 hat. No, sorry, 0. Because there is no F1 there. So that is 0 plus L by 6 F2 hat plus L by 3 F3 hat. Okay. Plus, plus, plus. Okay. I am now going to do the third term, but I can't really make progress with the third term. Why? G is not known. So unless I take a specific source term, I can't make progress. So only when we take up a problem, when I specify what is G of x, I will be able to find what is the loading term to which this system is responding. So we will hold it on. So G of x, G terms plus boundary condition here. Okay. So these terms will be here. This G terms and then this boundary term. I am not going to make headway right now. So let it be like that. Okay. So I am going to focus my attention onto these three terms because that is very important to understand. In the remaining time, we have another 15 minutes. So I will be able to focus on this. Up to this, is the procedure clear? Now, given any differential equation, you should be actually be able to develop finite element formulation. Whether you are trying to simulate a manufacturing process, you are trying to solve a computational structural mechanics problem, you are trying to find electromagnetic fields inside a motor to design the most efficient motor that you could get. Take the governing differential equation, just develop the finite element formulation. But in this way we have cast it right now, the beauty of the method is not really coming out fully. Okay. So I am going to now cast it in matrix form and then try to make you appreciate how the structure is evolving. Structure of the equations is evolving in a very repetitive manner. Okay. So stay with me for that part. So I will erase this now. We don't need this part. So what I am going to do is to write these three equations in the form of a 3 by 3 matrix, 3 unknowns, 3 equations, 3 algebraic equations. So I can write it as a 3 by 3 matrix, right? So I am going to do that. So see what I am going to do. A by L, this will be multiplying, sorry, F1 hat, F2 hat, F3 hat. The left hand side we are writing first. So A by L, I will take it out, it is common in all the three. So A upon L. So it is 1 minus 1 0 minus 1 1 this is what you have got in the left hand side, correct? So I will further draw your attention to this pattern that is emerging now. Okay. A by L, 1 minus 1 minus 1 1. Same thing repeated for the second element, 1 minus 1 minus 1 1. Okay. This is equal to B by 2 same thing. I am going to multiply by F1 cap, F2 cap, F3 hat. So this would be minus 1 1 0 minus 1 1 minus 1 1. Please see if I am making any mistake, just check that. Minus 1 1 minus 1 1 0 minus 1 1. So now you know why I have not struck off and written it as 0. Okay, I could have easily written this as 0, F2 minus F2 is 0 anyway, right? I intentionally did not do that to bring out this pattern for you. Whatever be the result, final result, that's okay. But the pattern is what you have to see. Plus one more matrix, C times. So C, shall we take L by 6? then it would be 2 times. Okay, CL by 6, I will take it out. F1 hat, F2 hat, F3 hat, plus additional terms are there. We are not yet discussing the additional terms, so I am not writing anything there. C times CL by 6, so 2 times 1, 0, 1, 2 plus 2, 4, so 2 plus 2, 1, 0, 1, 2. Okay. Now if I, instead of this way, if I present it in this manner, now the pattern in the equations is coming out more clearly. Okay. So this is belonging to the first element everywhere. This is belonging to the second element. Okay. So is this pattern equations clear to you now? Okay. So what we are really going to say is that I have formulated a linear one-dimensional element, correct? 2 nodes, any variable f1, f2. It could be temperature, displacement, whatever it is, fluid velocity, whatever be the physics of the problem, whatever be f. Okay. So the equations are going to be repetitive. As long as it is a linear element, I really don't need to do all these computations. I have for one element these computations, A, B, C, whatever matrices I am getting for one element, then I know that for the second element also it will be the same pattern. If I were to take the third element, it will be again repeating 200 elements, 200,000 elements. It does not matter. What would change? Of course, for convenience now, I have taken L to be the same. So they came out. But I can write it in a small computer program. Whatever be the length, it can take that as an input data from you and compute the element level matrices. So I want you to now think in terms of element level equations, so to say, element level matrices. This is the system level equation, system level matrices, but element level, you can think of these element level matrices in a chota computer program. So over the next few days, if you pray for Ganpati Bappa, you can actually create your own version of a linear finite element code. For a problem of structural mechanics, heat transfer, fluid mechanics, electromagnetics, does not matter. You can have your own code. All these packages that you probably have been using knowingly, unknowingly for various problems over the years are actually developed by people like you only, right? So you could take up a small Python program with these element matrices and then if I were to say now 3 elements, how many, what would be the size of this matrix? System matrix 4 by 4. Okay. And how would be that third equation coming? It would add to the leading diagonal one more submatrix like this, 2 by 2 matrix, 2 by 2 matrix, keep on adding it along the leading diagonal like this. You can have any number of elements. So, okay. So, you are now able to actually solve using linear finite element any one dimensional problem represented by this generic second order ODE that we started with, given A, B, C, whatever. Of course, we haven't yet worked out G, so we will do that later on. G we have to do, and then we have to actually solve these equations. But that is okay, we know how to solve algebraic equations, so I am not going to be too much worried about it. But you see now the power of the method. We started with the governing differential equation. We were trying to find approximate solutions. We proposed weighted residual method. We proposed Galerkin's weighted residual method. Now you can wonder why Galerkin suggested W be same as F. You get that? Do you see why Galerkin would have thought through and said you could solve using W being same as the trial functions in the way in which he proposed his weighted residual method? What is the advantage we got at the end? When you look at this matrix, what do you find? Pattern, repetition, okay. In the matrix that you would have got even if you had not used W to be same as F. But because I used W to be same as F, what happened in the integrations? X by L, 1 minus X by L, what happened? Huh? It got squared, okay. What did you finally get in the matrix? What do you see? Huh? Similarities, okay. Okay, some letters are matching, okay. Huh? Symmetric matrix, right? You got a symmetric matrix because you are meddling with integrations of X by L, 1 minus X by L, 1 minus X by L into 1 minus X by L, then X by L squared. So, some terms are coming in the leading diagonal, other cross terms are always X by L into 1 minus X by L or other way around, 1 minus X by L into X by L. So, your cross diagonal terms turned out to be the same. So, you ended up with a symmetric matrix, okay, fine, okay, in this and in this. But of course, that advantage is not carried over here. Why? So, you can think about it, it is a little, you can introspect why some terms in the differential equation. So, it is not just Galerkin's idea of W being same as F, it also depends upon the nature of the differential equation. So, some terms in the differential equation, d squared f by dx squared gave you this, f gave you this, but when you had df by dx, that did not give you this symmetric matrix. So, some terms are not giving you symmetric matrices, but if you are lucky, your equation is good, differential equation is initially good, you follow Galerkin's idea of W being same as the shape functions, then you would get all of them to be symmetric. When it is symmetric, then you know the computational storage advantages and solution advantages, all those things are there. But just one more point I want you to keep in mind before we wind up. So, imagine now, do a thought experiment. I have 100 elements, exactly the same calculations I will do, 100 elements, or let us say 99 elements, so that what will be the size of the matrix? 100, 100 by 100. How will be the structure of that matrix looking like? Let us focus on just left hand side. Okay. How will that matrix look like? 100 by 100. You imagine the numbers now in that 100 by 100 matrix. What can you tell about that? It's symmetric. It is 100 by 100. Okay, what more? Diagonal elements? Rest all? Rest all will be 0. In this case, for example, -1 hai. -1 hai. Center element will be the diagonal element. It is not called center element. The leading diagonal element, principal diagonal elements, okay, will be dominant. Okay, fine. Then what else you can tell? Where focus on, yes, anybody? What else can you tell about the nature of that matrix? How would where would the zeros and non-zeros elements will be? That's the crux.
The element just next to the diagonal one.
Somebody said tri-diagonal. Did somebody say, did I hear it? Who said that? Yeah, tri-diagonal means what, boss? What did you mean by that?
Diagonal dominance will be 3 lines.
So non-zero elements, or if you look at, imagine the 100 by 100 diagonal element, line, one below and one above, only will be non-zeros. Rest of them will all be zeros. So it is said tri-diagonal matrix. If you think in terms of a carpet being laid here, red carpet, that width of the carpet will be just 3. But the carpet is symmetric. So actually the width will be only 2. I need to know what is the leading diagonal element and what is this off diagonal element. That's all. Rest of the zeros, anyway they are zeros. I don't need to even store them. And if we are lucky, I don't need to even process them. Where from in our formulation, where from did this feature come? For the symmetry, we said it is from the term in the differential equation and Galerkin's idea of using weight function to be same as trial function. Now, from where did we get all these zeros bunched and non-zeros bunched towards the principal diagonal? From where in the formulation did this feature come? We are interpolating only between 2 values. When I wrote this right top, only in the first element, second element it is 0. Okay. First element this was 0. So the influence is only of the neighborhood, not something far away. So that is captured or reflected in the mathematical equations as the coefficient corresponding to that interaction in the matrix to be 0. That is another power of this method, that you are getting sparse matrices, lots of zeros. Okay, fine. So slowly you will start appreciating how and why this method became so powerful for all computational analysis. Okay, so we will stop here and continue in the next class.